Hello world, in today's video we're going to continue talking about the universal gravitational law. The question says determine the distance between the center of the moon and surface of earth if the force experienced by the moon due to earth is that much. So on that statement we are looking at force exerted by earth on moon, because this force is being experienced, it's being felt by the moon. So there are two objects of interest here. The first one, we have the moon. What do we know about the moon? Let us see. At the bottom, we are being told to take the mass of the moon, mm is mass of moon, as 7,35 times 10 to the power of 22 kilograms. The other object of interest, that is earth. What do we know about the earth? We actually know a lot of information about the earth. If you go back to the statement, you'll realize that there's no information that is given about earth. This is because information about earth is always given on the data sheet. So from the data sheet, the mass of the earth is 5,98 times 10 to the power 24 kilograms. And the data sheet also provides us with the radius of earth, that is 6,38 times 10 to the power of 6 meters. When you solve the universal gravitational law problems, number one, I said you must draw a sketch for yourself. Draw these objects, and on your diagram include R. What is R from this formula? We have said that from the universal gravitational law in mathematical form, R represents the distance between the center of object 1 to the center of object 2. In our case, that will be the distance from the center of the moon to the center of the earth. But what are we being asked to calculate? Are we being asked to calculate R? The answer is no. We are being asked to determine the distance between the center of the moon from here to the surface of the earth. So that is the distance that we are being asked to calculate, and I'm going to call it D. Okay, so we can include the final distance, this from the center of this circle representing earth to its circumference. From maths, the distance from the center to the circumference, it's called radius. In maths, they represent radius with small r, but because we are using the small r for something else, I'm going to use capital letter R for the radius. Radius of what? The radius of the earth. Please note that the universal gravitational law formula does not give us D. It gives us small r. Every time you use this formula, it will give you the distance, the center to center distance. When you sub into this formula, you need to sub in the center to center distance. So if we find the center to center distance, then we can find an expression for the small r. R from the diagram is D plus R E. What this expression tells us is, if we find R, how are we going to find R? We're going to find it using that formula. And if we know RE, which we already know from the datasheet, then we can be able to calculate the distance T. Okay, so let us use that formula to calculate. Remember, the bulk of the marks, they go to formula and substitution. So we have F equals to G, mass of moon, mass of earth, divided by R squared. Do we know how much that force is? Yes, it was given as 19,87 times 10 to the power of 19. Do we know the value of G? Yes, we do. Again, from the data sheet. We know the mass of the moon and the mass of the earth. You can sub them there. Let me just erase this with a white pen. I just want to make some space for myself. Okay. There we go. Almost there. There we have it. Okay. So I'm going to sub in mass of Earth times 10 to the power 24, mass of the moon that is given there, divided by r. So now in r squared, in this formula we only have one unknown. So you can do this for yourself. R will be equals to, I'm going to grab my calculator, 0.67 to the power minus 11 multiplied by 5.8 to the power 24 multiplied by 7.35 to the power of 22 divided by 0.87 to the power of 19. So if I punch that on my calculator, I find that the center to center distance is 3.841 times 10 to the power of 8 meters. Now I can go back to this expression of mine and try to find the distance d. From that expression, if I make d subject of the formula, d will be equals to the center to center distance minus the radius of the earth. Do I know these two distances? The answer is yes. So I can sub them in there. So I'm going to have 3.841 times 10 to the power of 8 minus 6.38 times 10 to the power of 6. And if I sub in, I'm going to find that the distance that we are looking for is equals to 3.777 times 10 to the power of 8 meters. Okay, so in this problem, D was a center to surface distance. So I like to classify these problems based on the interpretation of the distance that we are working with. So if we look at yesterday's problem, we were given center to center distance to work with, or they could have asked us to calculate the center to center distance. So this type of example is the one that I would refer to as the center to center case. Okay, feel free to try out this exercise, by the way. But today, we are being asked to calculate center to surface distance. And this problem, I would categorize it as a center to surface problem. But it did not stop the examiner to ask us to calculate the surface to surface distance, the distance from the surface of the earth to the surface of the moon. If the examiner wanted that distance, then it means they would need to provide us with additional information. So we have said that in black, that is the center to center that we always get from the formula. Let us say the question required us to calculate surface to surface distance, which is surface to surface. Then we would require additional information. We would require the radius of what? The radius of the moon. To calculate that surface to surface distance, we would have to use a new expression, the radius of the moon plus the radius of earth plus the distance that we are looking for, which is the surface to surface distance now, is equals to r. And how do we calculate this distance? We know this from the universal gravitational law formula. This, we get it from the data sheet at the back of the question paper, and the examiner would have to provide us with the radius of the moon. And that type of a problem, I would consider it as a surface to surface. Please remember to draw your diagrams because they are the ones that make it easy to solve the problem. Okay, so we are going to look at one more problem. We're going to look at a surface to surface problem. Please feel free to pause and try out this exercise for you. itself. We are being told at what distance must a satellite of 80 kilogram be away from the Earth to experience a force of, I'm going to change that to, let us say, 700 newtons. Okay. So objects of interest, we have a satellite, yeah. And then we also have Earth. So we are being told that the satellite experiences a force of 700 newton. So that is a force exerted by Earth on moon. So now I'm interested in something else. We are being told that that force is 700 newton. And now I want to know the force that the moon exerts on satellite. I want to know the magnitude of the force. Feel free to think about it for a while. Okay, you guessed it right. The force will have a magnitude of 700 Newton. Remember, we are having Earth. Let us think of Earth as our object A, the satellite as object B. Newton's third law of motion says, if A, the Earth, exerts a force on the moon, then the moon, oh, why did I say moon? Sorry, I meant to say satellite, and I realized that I actually wrote moon here. That was supposed to be satellite. My apologies, satellite. Okay. Newton's third law says if object A, which is the Earth, exerts a force on object B, which is the satellite, then object B, the satellite, will simultaneously exert a force of equal magnitude but in opposite direction on object A, which is the Earth. What is important about these two forces is that they are Newton's third law pairs, they are action-reaction forces. What are the properties? They have equal magnitude in opposite directions. So I have applied Newton's third law of motion over here to get to my answer. So what we are seeing here is if object A exerts a force on object B, object B will simultaneously exert an oppositely directed force of equal magnitude on object A, irrespective of whether the two objects are in contact or not. I hope that part is clear. Okay. So now let us go back to our problem at hand. So what do we know about the Earth? Remember I said that the mass of the Earth is always given on the data sheet. The mass of the Earth is 5,98 times 10 to the power 24 kilograms. Mass of the satellite, that was given as 80 kilogram. So if you compare the satellite and the Earth, I want to write the mass of the Earth in standard notation. That will be 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24 kilogram. That will be the mass of the Earth. So look at how large the mass of Earth is in comparison to the mass of the satellite. It's almost like comparing a grain of rice to an entire stadium. So because this satellite is so small, we can treat it as a point particle. Yeah, perfect dot there. That is a point particle over there in case you're not seeing it. When we talk about point particles, they are so tiny, we assume that they have no radius. The radius is so small that it is negligible. Okay, so what will be our distance? R, the center to center distance, because this does not have a center. We are going to have this as our R from the universal gravitational law. But what are we being asked to calculate? We are being asked to calculate the distance. What distance must the satellite be away from the Earth? So we want to know how far the satellite is from Earth. So that is the distance that we are looking for. So over here we are looking for a surface to surface distance. Hence, I called this a surface-to-surface problem. But what else do we know? We know the radius of the F. So we can find an expression for D. We know from the diagram that D plus the radius of the earth will give us small r. So if we find small r, we can make D subject of the formula. That will be r minus the radius of the earth. Where do we get this? We get it from the formula, the universal gravitational law in mathematical form. Now we can get started. We know the radius of the earth. We said that was 6,3 times 10 to the power 6 meters. So to find small r, we're going to make use of this formula. R squared. What is the force? I said let us change it to 700 equals to 6,6. 7 times 10 to the power minus 11. Mass of satellite, 80 mass of earth. Okay, divided by r squared. Then if you solve for r, you will find that r will be, let us see, just quickly grabbing my calculator, divided by, okay, so I find that this is 6,752 times 10 to the power of 6 meters. So I'm going to go back to that expression and sub this in. It means D is equals to R, which is 6,752 times 10 to the power of 6 meters minus the radius of Earth minus. By the way, my apologies. When you are given the radius of Earth, please check if it's given in meters or in kilometers before you sub in, because some of the data sheets they give the radius of Earth in kilometers. So that will be your answer there. How do you know if the problem is not a center-to-center problem? If the problem is a center-to-center problem, then the marks will range from 3 to 4 at worst. That's how you know it's a center-to-center problem. But the minute the mark allocation is 5 or even more, then you know that that is not a center-to-center problem and you need to take into account other things. But to always be on the safe side, draw the diagram before you answer the question. Okay, so I just want us to take a look at this question and call it a day. Okay, so it says, which of the following graphs represent the relationship between the gravitational force F between 2 points and the distance r between the objects? Okay, so what we can clearly see is they are plotting, from just looking at all these graphs, they are plotting graph of F versus 1 over r squared. How do I know in all of those graphs F is on the y-axis, while the reciprocal of r squared is on the x-axis? So you return to the formula. F is equals to g m1 m2 over r squared. And then you find this 1 over r squared factor. So you have F equals to g m1 m2 multiplied by 1 over r squared. You can make the replacement. So this will be y equals to, this we plotted along the x, that will be x. So everything else, I'm going to replace it with a constant variable. I'm going to call it b. And from this, we can clearly see that that graph is meant to be a straight line graph. So that's how we rule out the other two. So this option is out, this option is also out. So now we need to check which one is correct between B and C. If we look at B is the gradient. So the gradient of this graph, gradient is equals to g m1 m2. What we know about the mass is that it's a scalar quantity. Their masses are always positive. G is also a positive constant. So what it means is A is greater than 0. It's positive. If the gradient is positive, it means we have an increasing function, and that's how we get option C. In the next video we are gonna attempt to solve this problem. Okay, we're gonna do some application in tomorrow's video, or in the next video rather. Thank you so much for watching. Until we meet again.